yesterday or day before yesterday, PN junction Zener diode is also same as PN junction diode only, but this will work under reverse bias condition. Under reverse bias condition, actually this will operate under reverse bias condition only. Okay, so at just yesterday we have also studied Zener breakdown. So this diode will work near the Zener breakdown, near the Zener voltage or Zener breakdown voltage. Okay, Zener voltage. So little bit. Okay, there will work. Okay, so why we are using this one? Actually, what is the use of the Zener diode? Okay, what is the use of Zener diode? We will see that one. Why we are operating in reverse bias? Okay, what is that? We'll see. Okay, so here Zener diode also same working is same as PN junction diode only. Okay, same as PN junction diode only. Okay, is it clear my voice to you? Is it clear, guys?
Yes,
Is
sir.
it? Yeah, okay, thank you. So same thing. So Zener diode same as like a PN junction diode. Here also you will take P and N type semiconductor. The symbol is just like this is the plus and minus general diode. This is general PN junction diode. Here Zener diode symbol also very easy. Just you take the same as this thing, but here you write like a, this kind of things. Okay, plus minus. Here just like you write Z. Okay, Z type you will write in the symbol. Instead of straight line you write Z type. Okay, just like this is the Zener diode. Okay, symbol of this one is this. Okay, so now working is same. Okay, first before going to how it will work, we'll see first thing. Okay, so when you this Zener diode will work is in same reverse bias direction, reverse bias. So here if you draw IV characteristics, while discussing IV, I will go through this band bending in this thing. So IV when forward bias, this is plus voltage. Okay, plus voltage means that is forward bias condition. Okay, up to certain voltage it will, there is no current because we know yesterday also we discussed. So it is some of electrons overcome the barrier or potential light, then only we will get the current in a device. Okay, this is in forward bias condition. So this is same as please mute, same as like our PN junction diode only, normal or conventional PN junction diode only. But in reverse bias also this IV characteristic looks like the same. Okay, up to certain voltage, there is no current in reverse bias. This is in case of reverse bias voltage we are applying here reverse bias. Same, it looks like same, but it will start at a certain particular voltage. Electrons gain sufficient energy or holes gain sufficient energy from external electric field or external potential. Okay, once they get energy, so they will overcome the barrier and will get the current. Then it will slowly start increasing. After that, a rapid increase will be there. So here if you see here, you see in the reverse bias curve, this is breakdown voltage, you can say VZ. But here this is threshold voltage in forward bias. Okay, threshold voltage or knee voltage, whatever you can say. So why we are, the main advantage or main application of this one is, so for a small voltage, you can say small voltage, there is a huge increase in the current, so here voltage is almost stable. Almost is stable means very less change is there. For a small change, here you can see reverse bias curve. Suppose here 0 volt. Suppose this is 1 volt, or this is 2 volt, this is 3 volt. So after 4 volt also it is increasing. Okay, rapidly increasing. So for a small change in voltage, we are observing huge current in a device. That's why this is mainly application or advantage of this one is, you want to check the voltmeter, you want to check the stability of voltage, or you want to use in a devices voltage regulators. Suppose you want to control voltage. In that case, you can use this Zener diode. The main advantage of this one, even voltage is small, you can absorb huge current in a device in reverse bias condition. Okay, that is the main advantages. Okay, but in forward bias, it is same, looks like same as conventional PN junction diode. There is no change up to certain voltage. There is no current. No current. It's not correct one. Very small current here. Like current is like 10 power minus 12 amps. Okay, that is very less. Minus 12 to minus 15, minus 15 or minus 13 like that. It's very less current. That's why it is a negligibly small. Okay, this one here also reverse bias up to certain breakdown voltage. There is no current. That means very less current is there. That is also like 10 power minus 2 to minus 13, minus 12 to 13. That is, you can say, saturation current. Here this is indicates I0. This small current, you know, this small current we are calling saturation current. This small current. So this saturation current always should be less. Then only our device is perfect device. This is due to leakage of the charge carriers. Leakage of the charge carriers. So suppose you have a device, you are applying reverse bias, but there is a some of the charge carriers diffuse also, right? So we'll see that one. Okay, so we'll see the why this leakage current is coming. So why this leakage current is coming? Suppose you are connected device here in reverse bias. Suppose in reverse bias, here you are applying some voltage. Here you are applying some voltage. This is P and N, but because here only minority carrier. I will take a bigger diagram, then it is clear to you. So we will see the working of this one and leakage current also. I will draw a little bigger diagram. So generally in P and N type semiconductor, we will take little bit higher doping. Okay, if you increase the doping in P type semiconductor, what
Sir,
happens?
battery low. I will rejoin again in 5 minutes, sir.
Okay. So in P-type semiconductor, the if you increase the doping, what happens? Doping is increasing. What happens now? Please tell me. Answer this one. Suppose we are taking P-type semiconductor, where impurities are increasing, or doping is increasing. What happens? If you increase the doping, what happens? Semiconductor.
Conductivity increase.
Please tell me. Why conductivity is increased?
Impurities.
Yeah, that is right answer only. Why? So we are okay. We are increasing the impurities. That means we are creating more charge-free charge carriers. Suppose if P-type, we are creating more number of holes. Suppose if N-type, we are creating more number of free electrons by adding impurities. That's why if impurities are adding or doping is increasing, charge carriers will increase. Free charge carriers will increase. That means conductivity of the semiconductor will increase. Okay. Same thing here also. The Fermi level also closer to the this conduction valence band in p-type semiconductor. Same thing here also happens. Here also the conductivity close to the conduction band in n-type semiconductor. Okay, now you join these two semiconductor in reverse bias. Just you join. Okay, just you join. Okay, just you join here. Okay, this is the reverse bias. Okay, so here main thing is that in generally reverse bias or Zener diode will operate little bit P and N will take little bit higher doping semiconductors. Then this ferro level is close to the conduction band for N-type semiconductor, and it is close to the valence band for P-type semiconductor. This is EC, EF, EN. Okay, so here what is happening? EB. So here we are giving reverse bias, right? Reverse bias voltage. Okay, reverse bias voltage. That means okay. So reverse bias voltage. Here see electrons direct jump into the in this conduction band of the n-type semiconductor. This is electron tunneling. You can say electron tunneling. Electron tunneling process happens in high reverse bias voltage. If you increase the voltage or increase the reverse bias voltage, that is VR. If you increase the reverse bias voltage, what this happens? most of the electrons, bound electrons in p-type semiconductor, instead of going conduction band of the p-type semiconductor, they will tunnel into the n-type semiconductor. So if you keep increasing the voltage, this electric field or voltage, more number of at a time, more number of charge carriers will tunnel to this semiconductor. So why this is tunneling? Because suppose if you take a little bit higher doping, the depletion width also decreases. Depletion width, doping is increasing means, doping increases means the depletion width will decrease. Okay, that we'll see. Just a second here, I will draw. Suppose if this is just I am drawing here again. So here you are. So why the doping increasing means depletion rate is decreasing or narrowing. Suppose here you have a PN type semiconductor. Okay, this is okay, this is interface minus and plus charges. Okay, here P and N. Suppose if you increase or doping is increasing or impurities are adding, what happens? We are creating more number of holes. More number of holes in a P-type semiconductor. At the same time, if you increase the doping towards the N side, doping is increasing means we are creating more number of electrons in N-type semiconductor. That means this we are increasing a more number of electrons. These electron will combine with donor atoms in N-type semiconductor, and these charges will compensate. Charges will compensate and become a neutral atom. So this depletion width will reduce. Here charge density will reduce and depletion width also reduce. Similarly, so this p side, towards p side, this negative charge density, where more number of holes are there, by adding more number of doping atoms or impurities, we are creating more number of holes. These holes will recombine with positive negative charge density. Holes will recombine negative charge density, and this will become a neutral region. So like that, if holes will combine with negative acceptor density, that will become neutral. Okay, and other side, if electrons will recombine with positive charge density, it will become neutral. So whatever the region beyond the depletion region is neutral region. You say this one is neutral region. Okay, beyond the depletion region, the whatever the region you can say that is depletion region, beyond the depletion region is neutral region. There equal number of electrons and protons will be there. There is charge is neutral compensated. Okay, so if you increase the doping, the depletion width will decrease. So if depletion width will decrease means, instead of going this one instead of going to conduction band of same semiconductor, suppose if you take p-type semiconductor, electron break the bond and leaves the hole in valence band and jumps into a conduction band. This is general process, right? Generally, what happens if you take any semiconductor, if you give some energy, bound electrons break the bond and jumps into the conduction band, leaves the hole in valence band and create free hole in the conduction band. But if you increase the doping and doping is increasing here, doping is increasing, and we are applying high reverse bias voltage. In that case, what happens? If doping is increasing means the depletion width become narrow. So whatever electron, see, this is higher height. This is higher height compared to this height. So suppose here one height is this path is 1. Here path is 2. Just I am taking path 1 and path 2. Path 1 and path 2. Can you see path 1 and path 2? I have written. Can you able to see path 1 and path 2? Are you able to?
Yes, sir.
Yes, sir.
Yeah, okay. Please respond. Okay. See, electron seeing this is path 1 is higher width, higher height. To jump from valence band to conduction band along path 1, they see higher height, okay, compared to path 2. So that's why after breaking bond, they will jump into conduction band of n-type semiconductor along path 2. That is tunneling process. Why? Because the depletion width is lesser than the band gap, or you can say path 1 width is higher than the path 2 width. Path 1 width is greater than path 2 width. Sorry, path length. Okay, just a second. Length of the path 2 is lesser than the length of the path 1. That's why electron, after breaking the bond, they follow the easy path. Easy path. They follow the easy path. That's why here path 1 is longer length. Suppose this is 2 electron volts. This is 2 electron volts. This will be lesser than that. Okay, maybe 1 electron volts. Maybe 1 electron volt. So here path 1 is length is greater than path 2. So that's why electron instead going to the conduction band of p-type semiconductor, electron prefer to go to the conduction band of n-type semiconductor. That is, electrons are tunneling. Electrons are tunneling through depletion region, through narrow depletion region. This is why once you increase the electric field, large number of charge carriers will cross the barrier or cross the depletion width, enter into n-type semiconductor. Because of this electron tunneling, we are observing huge current in a reverse bias voltage or in breakdown after breakdown voltage. That is why in a curve you can see very abrupt increase in the current you are observing. Okay. So why electrons are tunneling here means there suppose depletion width is lesser width, narrowed, because we increase the doping in Zener diode, little bit higher doping will take. Because of this doping, more number of electrons are tunneling from p-type semiconductor to n-type semiconductor. How these are tunneling? Valence band of p-type semiconductor to conduction band of n-type semiconductor. Because of this tunneling, we are observing huge current in a semiconductor, huge current in a IV curve, huge current in a IV curve we are observing. Okay, right. This is the simply Zener diode. Okay, is it clear to you? Is it clear how this Zener diode is working? So this say because of that one here you see this is a Zener breakdown or Zener operating voltage, breakdown or operating condition. This is that's why here use current is, you can see current curve is very rapidly increasing. Current is very rapidly increasing. That is the reason. So very simple. Zener diode is a simple PN junction diode. It will operate in reverse bias condition. That is why we are using this is a in reverse bias means, suppose if you want to use in regulator voltage regulators or voltage, suppose you want to prevent from the damage of any meters or testing the voltmeters. So even you want to change small, you voltage should be stable. Then you can see current, how much current is changing. So small change in voltage up to Zener breakdown voltage or up to certain voltage, electron doesn't have sufficient energy, so that will not cross the barrier. Once you keep increasing the voltage at particular voltage, electrons or volts getting sufficient energy and break the bonds and jumping into the conduction band, and we are getting the current. Okay, this particular voltage we are calling breakdown voltage. Beyond this breakdown voltage, even small increase in voltage, there is a huge amount of current we are observing in a circuit. This current is mainly due to, if you increase the current, if you increase the voltage, whatever electrons in p-type semiconductor break the bonds in valence band, instead of going to the conduction band of same semiconductor or p-type semiconductor, this electron tunneling through narrow band gap, tunneling through narrow bandwidth, depletion width to conduction band of the n-type semiconductor. That's why even small increase in voltage, we are observing large number of charge carriers tunneling, large number of charge carriers tunneling. Because of this tunneling, we are observing for a small change in voltage, we are observing a huge current in a device. This is a simple working of the Zener diode. Okay, the applications are you can use in voltage regulators, and if you want to protect meters, you can use there, and also testing the voltmeters also you can use. These are the some applications. Okay, so is this clear to you, everyone? Zener diode working of the Zener diode. Did you get
Yes,
clear
sir.
idea how this will work? If you have doubt, you please ask me. Just like a PN junction diode only, but it will operate in reverse bias. That's it. Very easy. Just you. Very easy and important. Very easy and important. So is this clear, everyone? How this will doubts? You can ask me. Any doubts? No. At least you could follow the unit 2.
Yes, sir.
Unit. So okay, we have time. This syllabus is over, second unit syllabus. So we'll just I will explain just again PN junction diode, just this thing. Once I will repeat again, then it will be easy for you. So if you have any topic also, we'll get a revision time for revision. That time also I will try to explain. Okay. So here just I will draw these things, and I will explain. Okay. So mainly if you see here, PN junction means very simple. I'm drawing a very bigger diagram. See, you can clearly understand. So when you combine P type and N type semiconductor, P type and N type semiconductor. So in P type we know majority carrier holes. Majority carrier holes are there. Okay, majority carrier holes are there. So you draw it this one. And in N-type semiconductors also, we have majority carrier electrons. Majority carrier electrons. Okay. Majority carrier electrons here. Just I will explain now how the which carrier which transport is majority. Which transport is majority in forward and reverse bias. That already we discussed, but you may have small confusion. So these dots are electrons and these holes bubbles are holes. Okay, when you combine, because of the charge gradient, holes will leave the this region near the interface and enter into N-type semiconductor. So once this hole is leaving, here leaves a negative charge behind. Negative charge behind. Similarly, here hole also leaving because of the charge gradient and leaves the hole negative acceptor density. This charge is due to semiconductor always forms if you add third group element to fifth group element. So here suppose aluminum, gallium, whatever. Okay, similarly same process happens. Electrons will diffuse into N-type semiconductor, P-type semiconductor, and leaves a positive charge density. Positive charge density. Here also same thing. Some of the electron leave and leaves a positive charge density because of the higher charge gradient. This is diffusion process. Until charges are equilibrium, this diffusion continues. Okay. So whatever this charges induced left side and right side. So this region we are calling a space charge region. Space charge region. Okay. Space charge region. So here negative charge and positive charge densities we are seeing in the space charge region. Because of this plus and minus charge, there is a internal electric field. The internal electric field direction is plus to minus, plus to minus. Because of this internal electric field, what this will do? Here suppose some of the free electrons holes available in a space charge region. This electric field drift the or sweeps these holes and electrons. This whatever this electric field, induced electric field, sweeps the remaining free holes and free electrons in the depletion region. In the space charge region. So after forming the positive charge, negative charge, because of this positive and negative charge, we are having some internal electric field. This internal electric field sweeps remaining free electrons, free holes from the space charge region. Because of this sweeping, we are calling this region is a depletion region. Depletion region means sweeping of the charge carriers. There is no free charge carriers. Only this positive and negative charges are there. These are immobile. That means this will not move. These are fixed in a lattice. Fixed in a lattice. Because of this electric field also there is a built-in potential barrier or built-in potential, or you can say potential. Okay, once this region is forming, the electrons, suppose in n-type semiconductor, electron want to cross this barrier, but they will see some height. They will see some obstacle. Similarly, holes in p-type semiconductors also see some obstacle in depletion region. They cannot overcome this depletion width or height because they don't have sufficient energy. So for that we are giving some forward bias voltage and reverse bias voltage. So in forward bias voltage means, to forward bias means p-type semiconductor is connecting to plus terminal of the battery and negative terminal of the battery connecting to n-type semiconductor. Okay, plus, and this is forward bias condition. If you give forward bias condition, what happening? More number of holes will diffuse into the more number of holes type semiconductor and more number of electrons diffuse into p-type semiconductor. This is electrons and this is holes are diffusing. So here in forward bias what is happening? Depletion width is reducing, and because why? Because plus charge and minus charge is reducing. Because of this plus charge minus charge, depletion width is reducing, and because of this one, internal electric field also reducing. Internal electric field also reducing. Or resultant, suppose this is internal, this is external electric field. External field direction is plus to minus always. Okay, this is external. So resultant electric field direction also reducing. Resultant electric field also reducing. And because of this one, built-in potential also reducing. The height also reducing. So because of this one, more number of electrons will diffuse here and more number of holes will diffuse in this process. In forward bias, diffusion is the main dominant process. So what happens in forward bias? Please tell me. What happens in forward bias? Come on. Just now I explained. What happens in forward bias?
Depletion width decreases
Yes.
due to decrease in charges, negative and positive charge.
Yes.
And
Yes.
internal electric field decreases due to internal electric field.
Yes.
That potential also decreases.
Yeah, very good. And thank you, Vishwanath. Because of this one, you understand, right? When you applied external bias, more number of holes we are giving. These holes are diffused by, sorry, these holes are repelled by this positive charge. That means here we are applying same charge and holes also having same charge. That's why these holes will not come towards the battery. Holes always move towards the junction. And similarly, electrons also repelled by this negative potential, and this will also move towards the interface. So diffusion, so that diffusion is dominant in this process. Diffusion is dominant in this process. So this is the forward bias condition. In reverse bias, we will see. Reverse bias means P terminal is connected to negative potential and positive potential is connected to N terminal. Positive potential is connected to N terminal. So because of this one, negative potential is connected to P type. So holes having positive charge, and these holes are attracting towards the negative potential. Holes are attracting towards the negative potential. Similarly, this positive potential is connected to n-type semiconductor. N-type semiconductor majority are electrons. These electrons attracts towards the positive terminal. So that in reverse bias, the depletion width will increase. Depletion width will increase in reverse bias condition. In reverse bias condition, the depletion width will increase means here more number of negative charges induced towards P side, and say at the same time, more number of positive charges induced towards the P end side. Because of this more number of positive and negative charges, the internal and external field direction also same direction. Here internal field direction, external is this direction, and in the depletion width also internal electric field is in this direction. So resultant electric field also increase. In reverse bias mainly depletion width increased due to increase in positive and negative charges. Because of this positive and negative, electric field also increase in the depletion region, and built-in potential also increase because of this increase in electric field. So here mainly, so once this electric field is increasing means here this here electric field direction is plus to minus. Okay, this is internal electric field. This internal electric field, what this will do, main job is it will not allow electrons. It will not allow electrons to move towards the p-type semiconductor. Only it will allow minority carrier holes in n-type semiconductor. It will drift. So plus to plus. So plus charges are moving. Suppose electric field direction is plus to minus charge. So it will send only minority carrier holes in n-type semiconductor. Will drift or will push towards the p-type semiconductor. So holes are the minority carrier in n-type semiconductor. Once these holes will drift into p-type semiconductor, here holes concentration is increasing in p-type semiconductor. Similarly, here minority carrier electrons in p-type semiconductor, minority carrier electrons in p-type semiconductor will drift towards the n-type semiconductor. Only minority charge carriers will move one side to other side. Okay, because of this electron minority carrier electron from P to N, it is drifted. So here these electrons becoming a majority carrier. So because of this extending internal electric field, we are reducing the recombination losses. So here I want to tell you one point. While discussing device characteristics, we have studied this saturation current. This saturation current is due to leakage current in a device. Suppose here you see in reverse bias electrons holes are drifting. So here majority carrier electrons holes also there, right? This will also diffuse. Okay, this will also diffuse. So in reverse bias, see in suppose here in reverse bias electrons are drifting from N to P. And hole these holes are drifting from N to P, and electrons are drifting from P to N. This is drift process. In reverse bias mainly drift. Okay, mainly drift process. So this is main dominant process in reverse bias. But we know in n-type semiconductors also there is a electrons. This will also diffuse, and same thing holes from P also diffuse. Some of the charge carriers will diffuse from one semiconductor to other semiconductor. Because of this diffusion, we have some leakage current, that is I0. In forward bias also happens. In same case, if you take same case in forward bias also, electrons holes will diffuse P to N, holes will diffuse and electrons will diffuse. This is the diffusion process, is dominant process. Diffusion. Okay, but here minority carrier holes in n-type semiconductors also drift. These electrons will drift, and same thing minority carrier holes will drift. Okay, this is the drift process. Because of this drift process, this is a leakage current. Because of this minority carrier is some leakage current. So that's why we are observing leakage current in a device. You remember always this leakage current should be less. Then only our device